Okay, so we're on to chapter 13, and I have my whiteboard here like I'm Karl Rove or something. And chapter 13 goes more in depth into the physiology of the nervous system. And like we said last time, we're going to study the peripheral nervous system first because that is easier to understand and more understood by scientists, especially the way drugs alter it. So, we have our nervous system, and it's divided into the central and the peripheral. The central we talked about is the brain and the spinal cord. That's our control center. And the peripheral nervous system is divided into somatic and autonomic. And the somatic controls our voluntary movement. That is the nervous system that's going to be innervating skeletal muscle at that neuromuscular junction. And what's the neurotransmitter there? Acetylcholine. And then the autonomic nervous system is further divided into two categories, the parasympathetic and the sympathetic. And autonomic, I just think automatic. That's the easy way to remember it. And the parasympathetic is cholinergic, and the sympathetic is, I can never say this one, adrenergic. And I just think adrenal gland and the fight or flight response because what is it? Rest and digest for parasympathetic and fight or flight for sympathetic. So when I see adrenergic, I think the adrenal response, fight or flight. So a lot of times we hear rest and digest, fight or flight, which is a great way to remember parasympathetic and sympathetic. So when I say rest and digest, what comes to your mind? Hopefully the GI tract. Point being, though, we a lot of times associate the innervations of parasympathetic and sympathetic only with, parasympathetic controls the GI tract and sympathetic controls the heart rate or the adrenal response. And that's not necessarily correct. Most organs in the body are innervated by both. So that's going to come into play a lot when we talk about the cholinergic and the adrenergic. But it's important to remember that most of our body organs are innervated by both the parasympathetic and the sympathetic. And a lot of times sometimes they oppose one another, as in the heart, parasympathetic innervation is like putting the brake on your car. Even though it's a stimulus, even though it's activating the parasympathetic receptors with acetylcholine, it's slowing the heart rate. And then the sympathetic innervation at the heart speeds it up, right? When we have that fight or flight response, our heart starts really pounding. So the sympathetic and the parasympathetic innervation at the cardiac muscle are opposed. One speeds up and one slows down. Even though it's activation, it's agonistic in that they're binding to their receptors. The parasympathetic and the sympathetic have their own innervation. They're binding to their own receptors at their own neuromuscular junction at the cardiac tissue. They're both activating. Their activation has two different outcomes. So the parasympathetic, I believe the parasympathetic neurotransmitter at the heart is acetylcholine. And its activation in that specific receptor causes the heart rate to slow down. And now I'm not sure what the sympathetic neurotransmitter is there. It could be acetylcholine. But because it's binding to a different receptor on the cardiac tissue, it's speeding up the heart rate. Now, I think it's probably like epinephrine or norepinephrine, but the important thing to understand there is that acetylcholine is like the master key a lot of times, and it can bind to a lot of different receptors. But the different receptors, whether it be cholinergic, the muscarinic or the nicotinic receptors within the cholinergic system, they can cause a different effect. And that's the important thing to remember right now until we dive more into those receptors. One more thing that I want to talk about with the sympathetic and parasympathetic innervation is that it's not just like we fire a signal and that's it. Just like when I move my hand, I have a muscle signal. I have an action potential that's causing those muscles to contract, those somatic muscles. Well, if I didn't have some sort of action potential hitting these somatic muscles in my back all the time when I'm standing, even though I'm not thinking about it, I would fall over. Because we have to have some unconscious signaling of those somatic muscles to keep us erect when we're standing. We don't think about it, it just does it, right? So that's that autonomic muscle tone that we have. And that happens everywhere in the body. So most organs are regulated, they're innervated. Say this is our little stomach. That's a lovely stomach, isn't it? What's in here? If you haven't eaten recently, what's in here? That's a trick question. Nothing. It's empty. It's a hollow organ. But it stays hollow, right? It doesn't collapse. How does that happen? That's a great question. It's because parasympathetic tone. This is my stomach, and it's empty. It might be a little smaller when it's empty, but it's still a hollow organ. And this is my little parasympathetic innervation. And all the time, even when we're not doing the rest and digest thing, all the time, we have a little bit of stimulation. And that's causing tone. That's right, tone. T-O-N-E. Just like your muscles are toned. It's just keeping it in shape. So, most organs in the body are regulated by that parasympathetic tone. Now, there's one exception. Do you know what that is? Possibly, maybe not sure. Okay, the one exception to our tone, see if you can guess. Blood vessels. Blood vessels, they're hollow too, right? They have blood in them. They're innervated by the sympathetic nervous system. So the sympathetic nervous system, that's our little sympathetic nerve coming down and innervating the blood vessel. And that regulates tone. That keeps a certain amount of tone all the time. Now, can anyone think of a place in the body that is assessing the tone of these vessels, or the stretch of these vessels? I'll give you a minute. Baroreceptors. Good job, you knew that. Okay, where are baroreceptors located? The carotid and the aortic arch, right? So our baroreceptors, they're like proprioceptors. They're, it's the easiest way, and this is an oversimplification, but the easiest way to remember, it's just like when we talked about the thermostat. The brain is our little thermostat. That's my brain. These are light-colored markers. It's going to be green. That's my brain up here. My little brain stem. So my baroreceptors are my proprioceptors in joints, or any sort of receptor that I have. That's going to be my little baroreceptor. It's sending a signal up to the brain. And that signal on this blood vessel involves sympathetic tone. So it's saying, hey brain, we got this much stretch, this much pressure. And the brain is responding. So if the blood is up to here, and it's moving really slow because it doesn't have that peripheral resistance, then the baroreceptor is going to send that message along that efferent pathway to the brain. And it's going to do two things. The baroreceptor is going to cause more sympathetic stimulation. That's going to be the afferent response. So it's going to cause vasoconstriction. And then it's also going to send a message remember, this is a sympathetic innervation. This is the baroreceptor. And this is the heart. And it's going to send a message to the heart to say, speed up. Kick it up, buddy. We're not getting enough blood. And the heart's going to pump harder. And cardiac output is going to increase. And that is sympathetic tone.